All right, well, let's get started. It's just past the hour. There may be some more folks joining, but I think we can get started. So welcome, everybody, to the Biocurator Working Group call. I'm Jenny Goldstein. Just to let you all know, I am recording this call, so it will be available if you want to listen in again or for other folks who are unable to join. So today, I'm delighted to introduce Erin Riggs, who's going to be reviewing the ClinGen Dosage resource. So many of you may know Erin already. She's really a force of nature within ClinGen. She's very involved in many different ClinGen working groups and expert panels, including, but by no means all, the Gene Curation Working Group, Education Coordination and Training Group, ID Autism, GCEP, Brett Angelman VCEP, and many, many other roles that she has within ClinGen. But she's also the coordinator of the Dosage Sensitivity Working Group and the Copy Number Variant Interpretation Guidelines Group, which she's going to be focusing on today. And she's the author of several papers on the clinical interpretation of CNVs. So, Erin, we're delighted to have you today to be talking about this topic. But before you get started, just a reminder to everybody to please mute yourselves unless you have a question for Erin. You can ask the question or you can type it in the chat box. But please just mute yourselves when you're not speaking so that we can avoid as much background noise as possible. All right, so thank you, Erin. So whenever you're ready, thanks for being here.
All right, thanks for having me, Jenny. There we go. Okay, so just to set the stage for what we'll be discussing today, we'll spend the bulk of our time focusing on the ClinGen dosage sensitivity map, but I've also been asked to talk to you about how you might incorporate those CNVs into other types of curation, in particular gene disease validity curation, as well as to give you a brief tutorial on how to find CNVs in ClinVar. And like Jenny said, if you have questions, feel free to ask. If we don't have time to get to all this, that's okay. Perhaps we can do some of it another time. So dosage sensitivity curation began in 2011, actually, as part of a project that many of our current ClinGen investigators were involved in, which was called the International Standards for Cytogenomic Arrays Consortium, or ISCA. And this was around the time that chromosomal microarray was first coming into wide clinical use. So labs were identifying novel copy number variants, or CNVs, on a regular basis. And, especially when this was new, it was kind of unclear how to assess these. And guidance at the time recommended that, that you assess the genes within the CNV and correlate with established clinical literature. Asking the question, do we have any evidence to suggest that loss or gain of even a single gene within the region results in a clinical phenotype? However, there weren't really any specific recommendations to tell people how they might go about doing this. So the dosage sensitivity curation process was developed in order to facilitate this for the genomics community and promote classification consistency. And we are getting quite a bit of background noise, so if people could just mute, that would be awesome. So to illustrate and expand upon what I just said, knowing whether a particular gene within the CNV is haploinsufficient or triplosensitive may help drive the classification of that CNV and others involving that gene. So just to give you a graphic representation, at the top of the slide, there are 6 example genes, and at the bottom in red are 7 deletions overlapping each other and the genes to various degrees. In this figure, we don't know the classification of any of these CNVs. However, if we have evidence to suggest that gene 3 is a known haploinsufficient gene, we can update the classification of all the deletions that completely include that gene to pathogenic. In this figure, that includes CNVs 1, 2, 3, and 7. And even though CNVs 5 and 6 overlap the others, they don't include gene 3, and so we can't classify those as pathogenic without further evaluation. You can imagine that this type of information could also be used to resolve discrepancies between labs. So, say CNVs 1, 2, 3, and 7 all had different classifications from different labs. The dosage sensitivity curation for gene 3 could prompt a resolution of those discrepancies. So when we started dosage curation in 2011, we were initially focused on evaluating the 370 or so genes that were getting targeted coverage on the ISCA 180K array design. And this design was developed by the ISCA consortium years prior, using a method that might sound eerily familiar to people, working in labs, just simply collecting all the genes recommended for targeting at the time, combining them all together without really much concern about the evidence. So I'll say that after the first round of evaluation, we actually ended up finding no evidence to support about 120 of those genes and recommended removal of targeting on future array designs. After we completed that effort, we focused for several years largely on neurodevelopmental disorders, using data coming from other projects such as DDG2P in the UK as a way to triage genes for evaluation. Today, we have 3 different active subgroups. We maintain our focus on the neurodevelopmental disorders because this remains a common reason for chromosomal microarray referral and really genetic testing in general. We also have a subgroup focused solely on recurrent regions. These are genomic regions that occur frequently within, or CNVs around these regions occur frequently within the population due to specific genetic architecture around that region. So for example, segmental duplications. And even though we do have a lot of data surrounding many of these regions, they're often challenging to assess because they're frequently associated with reduced penetrance and variable expressivity. Our newest subgroup is focused on evaluating dosage sensitivity for those genes implicated in hereditary cancer. Now, there are 2 types of dosage sensitivity records. We have records that are evaluating a single gene and those that are evaluating a genomic region. We most often evaluate single genes, but we do have a number of genomic region records, in particular those recurrent regions that I just mentioned. But we also have some other non-recurrent but clinically relevant regions. Each record is evaluated for both haploinsufficiency and triplosensitivity, so there are separate scores assigned for each of those on each record. And at this point, we've evaluated 76 regions and almost 1,400 single genes. So I'll note that we are currently in a transitional process period for dosage sensitivity. The type of evidence that were available to us and the ways in which we evaluate and apply that evidence has changed, since we first started doing this in 2011. So we're currently in the process of updating our scoring procedures to be more consistent with those put forth in the new ACMG ClinGen CNV technical standards. We've been utilizing a process that mirrors the recommendations in Section 4 of the CNV scoring metrics since approximately February 2019, and adjusting them as needed for single gene dosage sensitivity evaluations as opposed to a full CNV evaluation. So here I'm showing you our scoring scale, which remains unchanged despite the adjustments in the way that we arrive at the particular score. So the highest score is 3, which signifies sufficient evidence for either haploinsufficiency or triplosensitivity. Genes and regions that have less evidence receive lower scores, respectively. 2 signifies, there we go. 2 signifies emerging evidence. 1 is equivalent to little evidence, and 0 means that there's no evidence supporting dosage sensitivity that has been reported. There are a few additional scores that are intentionally not in numerical order with the others because they mean very different things. So a score of 40 is equivalent to dosage sensitivity unlikely, and this means that there's actually evidence against dosage sensitivity, so akin to a disputed or refuted gene curation. A score of 30 indicates that the gene has been associated with an autosomal recessive condition. It makes no assumption of the mechanism of disease, whether the autosomal recessive condition is caused by loss of function or any other mechanism. So this is something we're considering updating in the future to specify the disease mechanism if known, but for now, if you see one of those, don't read anything into it other than it is associated with an autosomal recessive condition. A score of -1 is something that we really just use programmatically within our system just to annotate those genes that we don't plan to evaluate, such as pseudogenes. And though the scores are remaining the same, one thing that's changing within the updated scoring procedures is how these scores might be utilized in the clinical context. Okay. So the main difference is that with our more stringent criteria, CNVs containing genes with a score of 2 that have been evaluated from February 2019 or later could be considered likely pathogenic. At this point, I'll walk you through our single gene scoring process. However, all of our evaluations, including the region evaluations, start with the same premise. When we're evaluating a gene or a genomic region, we're really asking ourselves two main questions. For haploinsufficiency, when this gene or genomic region is lost, does it result in a consistent phenotype? And for triplet sensitivity, when there's an extra copy of this gene or genomic region, does it result in a consistent phenotype? So our primary evidence is case data from humans. For the haploinsufficiency score, we're looking for evidence of loss of function, such as single gene deletions, exonic deletions within a single gene, or putative loss of function sequence variants, such as nonsense, that are thought to be undergoing nonsense-mediated decay. Other types of sequence variants may be considered if there's strong functional evidence suggesting loss of function. The type of evidence that we consider for triplet sensitivity, on the other hand, is much more narrow. Really, we're only considering whole gene duplications involving only the gene under evaluation. And that explains why so many of our genes have triplet sensitivity scores of 0. We can't really rule out the effects of other genes in multigenic duplications, and intergenic duplications may in fact be acting as loss of function. We also don't consider gain of function sequence variants, which is actually a common misconception that people have. So just to make that clear, that's an entirely different disease mechanism. So in general, for both scores, we take a conservative approach. Only evidence involving that gene alone is considered. The following are typically considered supporting evidence, but not primary evidence. So things like the smallest region of overlap suggests that this particular gene is the causative gene, or evidence from a translocation case unless both breakpoints have been mapped and functional evidence suggests no effect of the second breakpoint, or unpublished evidence. This type of information can, of course, still be useful and can absolutely be noted on the record, but don't typically contribute to the overall score. Functional evidence, such as evidence from animal models, may be used to upgrade the score of a particular piece of evidence. Our original scoring guidelines were relatively simple. The score correlated to how many probands had been observed. So a 3 or more usually meant that there were 3 or more probands across at least 2 independent publications. If there were only 2 observed probands, the score was 2. 1 proband, the score was 1. 0 probands, the score was 0, etc. The score of dosage sensitivity unlikely was only used if there was valid evidence against dosage sensitivity, and gene associated with autosomal recessive disorder was assigned as the haploinsufficiency score when applicable. The main change to this approach is just removing that concept of a specific set number of probands driving the score. The other concepts still apply. So again, as I mentioned previously, our updated scoring guidelines are closely aligned with the new technical standards for CNV classifications, specifically category 4 of the scoring metrics, which is shown here. In our updated process, points are still awarded per proband, but the amount differs based on both inheritance and phenotype. So inheritance, we do have different scoring recommendations for whether or not the variant is de novo or of unknown inheritance, or if there's segregation among similarly affected family members, or apparent non-segregations. And in terms of phenotype, we do also have different scoring mechanisms in terms of if it's a highly specific, relatively unique phenotype, if it's consistent, specific, but not necessarily unique, and then if it's consistent but not highly specific and or with high genetic heterogeneity. A suggested number of points is provided for each category, and there's also a range to give you the flexibility to upgrade compelling pieces of information and downgrade information with less quality. The evidence points are tallied to help the curator arrive at a preliminary haploinsufficiency or triplet sensitivity score, and the curations are reviewed and approved by their respective dosage sensitivity subgroups. Next, I'll go into a bit more detail about the scoring process. Again, in general, points can be awarded based on both the specificity of the phenotype observed in the case and the reported inheritance information. So, a de novo case with parental relationships confirmed will score higher than a case with a similar phenotype but no inheritance information. A de novo case with a non-specific genetically heterogeneous phenotype, such as autism or developmental delay, would score lower than a de novo case with a more unique, less heterogeneous phenotype, like something like iris heterochromia and white forelock. Essentially, more weight should be given to cases where you can be more certain that a given phenotype is truly associated with your gene or genomic region of interest, and the extent to which other possible causes can be ruled out. So, for example, a case report in which the authors report a de novo variant identified on single gene sequencing in a proband with autism might not be a particularly strong piece of evidence regardless of its de novo status, just because autism has been associated with numerous genes, making it nonspecific, and based on the information provided, none of these alternatives have been ruled out. What if the reported phenotypes are varied and inconsistent? In this scenario, you need to consider whether this truly represents anti-evidence and warrants negative points, or if it simply represents a lack of information, too little information to make an informed assessment and warrants 0 points. So consider the following example. In the first scenario, you have a deletion of a particular gene that has been reported only twice in the literature, once in a 7-year-old with developmental delay and once in a newborn with a congenital anomaly. So depending on what information you have available, you might choose to score a scenario like that at 0 points, just because you don't really know if the newborn is going to go on to develop developmental delay. And you also don't really know if the older child was evaluated for the newborn's congenital anomaly. In the second example, say the deletion was now reported 5 times, at this time, all in older, well-phenotyped information. So maybe an adult with intellectual disability, an adult with a history of cardiac defect, normal development, an adult with a history of different kind of defects, and maybe genitourinary and normal development, and 2 general population individuals. In this scenario, you might feel more confident saying that these presentations seem disparate enough to warrant negative points. Variants of unknown inheritance may be counted in certain situations, such as in the setting of a highly specific phenotype. So, for example, it might be appropriate to use this evidence category when you're evaluating a relatively specific adult onset condition, where getting parental samples would be particularly difficult because parents are unavailable. Variants of unknown inheritance should not be counted as evidence in the setting of nonspecific phenotypes like intellectual disability or autism. Segregation of a variant among similarly affected family members can lend support to the argument that the variant could be disease-causing. But of course, it's always important to remember that segregation implicates a locus and not necessarily a particular gene or variant. So while the given variant may be segregating within a family, you can't really rule out the fact that it could be in linkage disequilibrium with the true causative variant. So we recommend a conservative approach and one that's consistent with the gene curation approach, if you're familiar with that, with at least 3 documented segregations among affected individuals in order to award points in this scenario. And we do also have the same recommendation of only counting individuals that are both genotype and phenotype positive, or individuals that are obligate carriers by virtue of their position in the pedigree. Instances in which the variant appears not to segregate with affected status need to be interpreted with caution. So apparent non-segregations include instances in which another affected individual in the family is found not to have the variant in question. So that's category 4I there on the left. Instances in which an unaffected individual is found to have the variant in question, and that's categories 4J and K, and those differ by the specificity of the phenotype. So in the first scenario, that category 4I, before considering this evidence against pathogenicity of the variant and assigning negative points, you really need to think about whether or not there may be biologically plausible explanations for this non-segregation, such as the presence of phenocopies. This scenario might be more likely to occur in the setting of disorders that are more common in the general population. So maybe, for example, breast cancer, and or disorders that are known to have both genetic and non-genetic causes. So maybe something like cardiomyopathy. Consider downgrading this evidence when phenocopies are a possibility. For the second scenario, categories 4J and K, you really need to think about whether or not that family member that was found to have the variant is truly unaffected. And this can be difficult to determine, particularly in cases ascertained through the literature, public databases, or even in your own internal lab databases, because it's often not possible to request additional clarifying information. Truly affected individuals might appear to be unaffected for a variety of reasons. So maybe in the context of variable expressivity, reduced or age-dependent penetrance, disorders with subtle clinical manifestations, incomplete clinical evaluation, or novel disorders in which the phenotypic spectrum has not yet been well characterized. The specificity of the phenotype plays a role in how confident you can be in that family member's unaffected status, and the recommended point values vary accordingly. So one example, if the phenotype that you are talking about is, say it's something like a rare eye phenotype that you can only appreciate with a dilated eye exam. If the family member was evaluated by an ophthalmologist with dilated eye exam and found not to have that eye phenotype, then that you might feel more confident awarding negative points. If, however, the family member was just evaluated by a general practitioner and it was unclear whether or not a dilated eye exam was performed, then you might consider downgrading that evidence. Other pieces of information that may support the haploinsufficiency evaluation, even though they're not necessarily used as primary evidence. So this includes haploinsufficiency predictors, such as the NOMAD PLI LUF scores and Decipher haploinsufficiency index scores. When these are in agreement and all indicate haploinsufficiency, they can be used to bump up or down genes that are on the fence between two scores. So for example, a gene has enough evidence to score right in the middle of category 2 and 3. And if the haploinsufficiency predictors suggest haploinsufficiency, the evaluation team might opt to upgrade to give it a score of 3. Caution should always be used, however, when deciding whether or not to incorporate this information. Think about things like genes that are associated with adult onset conditions might have lower PLI scores because reproductive fitness is not being impacted. Loss of function variance observed in the general population might be a different area of the gene than the loss of function variance in the affected individuals, the potential for false positives, etc. Other things to think about include common variation in case control data. If common variation is present at high frequencies over a particular gene, this might be information indicating that dosage sensitivity is unlikely. Some genes do have case control data available to support or refute dosage sensitivity, but as in gene curation, you should always consider the quality of the study before deciding how to incorporate that information. Our method for evaluating recurrent regions is also undergoing changes. I won't spend much time on this as it's still in ongoing development, but it more specifically incorporates results from case control studies, such as p-values and effect sizes. So I'll quickly walk you through a single gene scoring example. So let's take the gene ZNF462. So we have a couple of papers with case level evidence here, the first being Weiss et al. 2017. This paper describes probands from 6 families, 8 total individuals with predicted loss of function variance in the gene. And the phenotype per the author includes metopic ridging or lambdoid craniosynostosis, dysgenesis of the corpus callosum, ptosis, developmental delay with or without autistic features, as well as some dysmorphic features. When you actually look at what variants were reported in this paper, it was a mixture of sequence variants and there were also 2 copy number variants. The variants that are boxed in red are the variants that we would take forward for the dosage evaluation. We would not consider we wouldn't consider this first CMA variant from proband 4 because it included additional genes. And then the others are putative loss of function sequence variants. If you are wondering, which phenotype category should we be using for this particular phenotype, based on the first paper, the first 6 probands that were reported had a variable phenotype, including a number of non-specific features, so intellectual disability, developmental delay, autism, hypotonia, and some slightly more specific features, but not necessarily unique, so things like ptosis or metopic ridging. I would say at this point, just looking at the first paper, it's kind of unclear whether this is a consistent but variable constellation of findings or if they're unrelated. So additional cases might help clarify. But, however, being conservative from the Weiss paper, we know we have at least one 3 segregation family and at least 2 de novo loss of function variants with parental relationships confirmed because they were done on trio-based exome sequencing. Another paper was reported in 2018. This one talked about a de novo balanced translocation in a patient with intellectual disability, autism, with topic craniosynostosis and dysgenesis of the corpus callosum. The translocation breakpoints were mapped to KLF12 on chromosome 13 and our gene ZNF462 on chromosome 9. The authors assumed that haploinsufficiency of ZNF462 was causing the phenotype because of the previous clinical report, but they didn't do any functional studies to demonstrate this. And they also didn't do any functional studies to rule out the effect of KLF12. So really, we can't rule out the effect of this gene. So while compelling, this type of evidence would not be used for the dosage evaluation. We would certainly note it just to make sure people knew that this was out there, but it wouldn't count towards the final score. Finally, there was one more paper that came out in 2019, which described 14 additional individuals with loss of function variants in this gene. So that brings the total up to 24 people, including those from Weiss and the translocation cases. Interestingly, those additional individuals shed light on the phenotypic spectrum, and it looked a little bit different from what it was looking like from the first paper of 6 people. So in those first cases, it seemed like the metopic ridging was going to be a significant phenotype in kind of the spectrum because most of those people had it. But then when we found more people, we found that that was really only present in about a third of the cases, whereas the developmental delay was the more predominant feature in almost 80% of cases. So in the summary of the variants from that paper, 13 of the 14 were detected by exome sequencing, 1 was by genome sequencing. They were all putative loss of function variants. 10 of them were de novo. The paper made no comment on confirmation of parental relationships. 2 had unknown inheritance. 1 was paternally inherited, but that father did have a positive family history. He had ptosis that required surgery. And 1 was maternally inherited from a mosaic mother. So when you put everything together, even if you were being extremely conservative and counting this as a nonspecific phenotype and assuming the parental relationships were not confirmed if that was not explicitly stated, and not using the cases where other variants were identified and the effects of other genes could not be ruled out, we'd still have at least 2 de novo cases with parental relationships confirmed, at least 10 cases with parental relationships assumed, and 4 total observed segregations, giving you plenty of evidence to give this a haploinsufficiency score of 3, as shown here. So how do I access these dosage sensitivity curations? Well, they can be accessed in a number of ways. They are available through the Dosage Sensitivity Map website at the URL you see on the screen. At this site, the data is available for both the single genes and the recurrent regions, and you're able to search by gene name or by genomic coordinates. I'll note that this site will be moving to a ClinGen server in the near future, and you'll be automatically redirected to the new page, which will look and act the same from this site. Single gene dosage curations are also currently available on the ClinGen website, clinicalgenome.org, and at this time you can only search the ClinGen site by single gene. Recurrent regions, as well as the ability to search the ClinGen site by genomic coordinates, will be available in the future. And finally, the genes and regions that have gotten a score of either 3 or 40, which again means dosage sensitivity unlikely, are added to the NCBI study called NSTD45 on a quarterly basis. And that information is used to populate tracks on both the UCSC Genome Browser and NCBI's Variation Viewer. So here's a view of the current Dosage Map website and the current URL at the top. And again, remember, this site is going to be redirecting you to a new site on a ClinGen server shortly. In fact, they just started this process today. But it should still look like this and work just as I'm about to show you. The site is publicly available and updated with new curations as soon as they're finalized by the group. To search for something on this site, you can input a gene name or genomic coordinates, and your search results will look like this. So please note that the results are going to be displayed in two tabs. The first tab that you see includes individual genes that match the gene name you provide or that are included within the coordinates you provide. You'll notice that there are several columns here, and you can click on any of them to sort the table by that particular piece of information. You'll also note that some genes are designated as awaiting review and others are marked as complete. Only those that are marked as complete have been reviewed by the committee and officially closed out. And finally, if you were to click on that second tab, Region Issues, if there's a number in parentheses there, that indicates that there is a curated genomic region that overlaps the coordinates you provided. So be sure to pay attention to that if that's relevant to your case. Once you select the entry that you're interested in, you'll be taken to a page that looks like this. This is the top of the page. Note that we do post the date that this gene or region was last evaluated, and you'll want to pay close attention to that because if it was some time ago, you'll definitely want to do your own literature evaluation to see if anything's changed. You'll also be shown the haploinsufficiency and triplosensitivity scores right at the top for quick reference. And if there are any related curated genomic regions associated with a particular gene, it'll let you know there. If you scroll down to the bottom of the page, you'll see more detailed information. Again, this is organized in tabs. If you were to click on the first tab, which was called Genome View, you'd see a browser-based view of the region. The other two tabs contain the evidence for haploinsufficiency and triplosensitivity. So we'll just look at the haploinsufficiency tab for this particular gene. The first box outlines the PMIDs that we've counted as evidence for this particular gene. And there's a link out to the PubMed ID if you wish to look at it, as well as a short description of what we feel like is the relevant information. So here's that link out and the description. The bottom box, which is down here, contains information that may be of interest to you but may not have been a factor in the final score, such as additional phenotype information or cases that didn't conform to the original rules but are still of interest, etc. So do pay attention to this bottom area if there is one on the page that you are viewing. The page also contains a link to an FTP site. This FTP site is updated daily, and it includes bed files that you can use in the browser of your choice. Here's a screenshot of how the dosage results are displayed on clinicalgenome.org. This is, of course, the same information that's also available on the dosage site, but again, only includes the single genes, not the regions at this time. And finally, on a quarterly basis, genes and regions that have been given a score of 3 or dosage sensitivity unlikely are added to a data set in NCBI's DBVAR called the ClinGen Curated Dosage Sensitivity Map, or NSDD45. And this information can be downloaded and used to make tracks for the browser of your choice, and it's available as an optional track selection in NCBI's variation viewer. So now that I have told you about how the dosage evaluations are done and where you can find them, I want to talk about how they might be used in other ways besides evaluation of copy number variants. So in particular, how you might be able to use them in other ClinGen curations. So if a ClinGen curation activity utilizes case-based evidence, so if you're looking for a proband with a plausible variant and the phenotype in question, then you can theoretically use this information that's available on the dosage map. So you could consider it kind of like a starting point as you begin your search for cases. This type of information can at the very least point you in the direction of some useful articles, but could also help you establish the mechanism of disease if it is indeed loss of function or triplosensitivity. If you do decide to use CNVs as evidence in other curation types, such as gene disease validity, in general, you should be focusing on those CNVs that only involve a single gene. When other genes are involved, we can't really rule out their potential effects, which makes these cases less than ideal to count for evidence in other single gene evaluation settings. So it might still be useful supporting evidence to know. So for example, that individuals with large deletions over a particular gene demonstrated similar phenotypes as individuals with loss of function sequence variant in that gene. So that might be good to add to your evidence summary just as an FYI, but you might not necessarily be counting those for points in your evaluation. Currently, if you would like to include this type of information in, say, a gene curation, you will need an identifier. And if your CNV is already in ClinVar, that is great. You can use the ClinVar ID as you normally would. If your CNV is not in ClinVar, you would need to obtain an identifier from the ClinGen allele registry. So previously, the allele registry didn't provide identifiers for variants over 10 kb in size, but the allele registry team has been hard at work and has now developed the ability to accommodate variants over 10 kb, but they're currently working on supporting real-time registration of those types of variants. The GCI and VCI team is also working on being able to accept these new CNV IDs. So we'll let you know on a future Biocurator call when these capabilities are available. For now, if you already have enough evidence to reach definitive in a gene disease validity curation without incorporating CNVs, there may not really be a need to include them. If they are a frequent variant type, it might be nice to mention them in your evidence summary, but you might not want to include them as your scored evidence just for the limitations we just mentioned. If you do need CNV cases in order to maximize your scoring, what you can do for now is just describe the variants in the free text blurb, assess how many points each would be worth, and then manually adjust the classification if needed to reflect the addition of the CNVs. And just be sure to explain what you did in the reason for change field. So this is difficult to see, but this is an example of a gene disease validity curation for Orexin 1 and complex neurodevelopmental disorder, where we really did need the CNVs in order to maximize scoring. So you'll note that the classification actually needed to be modified from limited to definitive because the majority of the observed variants were in fact CNVs. And again, it's difficult to read, but you can hopefully appreciate how the curator described the CNV cases in the evidence summary blurb up here. So, you know, even though if you were looking at the scored table, you wouldn't necessarily see them because it couldn't officially be added, we've accounted for them here. So that's what you can do if you need to do that. All right, and then finally, I will provide you with a brief tutorial on how to identify copy number variants in ClinVar. So first, I do want to point out that yes, ClinVar does accept and display CNVs, and in fact, there are currently over 51,000 CNVs in the database. And this includes data that was previously submitted by the ISCA consortium project that I mentioned earlier. In addition to developing the dosage sensitivity curation process, this group really represented one of the first major efforts to publicly share results from clinical genetic testing. Again, remember, around the time this is happening, 2009, 2010, chromosomal microarray was first becoming widely used, and the same issues that came about when exome sequencing became widely used. People were finding variants they've never seen before, they weren't really sure how to interpret them, and we realized that sharing our information might help us with this. The idea of making this type of information publicly available for all to use and learn from was relatively novel at that time, and there were no clear-cut guidelines for how an entity such as NCBI would accept and display this information. And what I mean by that is information that was outside of the traditional research realm. ClinVar was not in existence at the time, so this type of data was accepted almost kind of as a one-off by existing resources such as dbGaP and dbVar. And I tell you all of this just so you can make sense of how this data is currently displayed in ClinVar and how or why it's still cataloged in other NCBI resources. So one example of how this particular data set is a bit different from others you may see in ClinVar is the fact that many of the submitters are anonymous and listed as things like ISCA Site 1, ISCA Site 2, etc. And this is because at the time it was thought by many institutions that this was necessary to protect patient privacy. Of course, over the years, positions on this have evolved, and we now believe that displaying the lab name confers no additional risk to patient privacy and in fact adds the benefits of transparency, being able to identify and resolve conflicts, etc. So one thing to keep in mind about identifying CNVs in ClinVar is that, while you can absolutely search ClinVar by genomic coordinates, the way that you enter them is different. And if you don't enter them correctly, you will not get the results you're looking for. Entering genomic coordinates alone will only search for exact matches, so literal exact matches with the numbers that you put in. You need to use the proper syntax in order to return overlapping results that people are typically interested in when they're looking for CNVs. So here's what you need to do. Note that the information specific to your search is in red, like the chromosome number, the particular coordinates, etc., and the quote-unquote commands that you need to give ClinVar are in blue. So you enter your chromosome number followed by a bracket, CHR bracket, then the word and, then your first coordinate, a colon, not a dash as most people are used to, the second coordinate, then bracket, CHRPOS 37, and bracket. And that CHRPOS refers to the assembly. You can edit the number there as you need, realizing that you'll need to use the GRCH numbering system. So to illustrate this point, we'll search for a region that I know has overlapping CNVs within ClinVar. If I enter the coordinates in the traditional method, as shown here, I get no results. In fact, ClinVar doesn't even recognize that the numbers that I have entered are genomic coordinates. When I search the same region using the proper syntax, I get 912 results. Note that it doesn't matter if you put spaces between your info and the bracketed items in the colon, but you must put a space before and after the word and. And realize that searching ClinVar this way will pull back any sequence variants in the interval as well. However, you can exclude many of these by using the filters on the left-hand side of the screen, which we will review next. And also keep in mind that you can use the filters to exclude CNVs by selecting kind of almost the opposite of what I'll show you next, if that is in fact what you would like to do. So this is just showing you what those results look like. The red box and arrow is drawing your attention to the location of those filtering options that I just mentioned. One option, if you're interested in narrowing these results to only CNVs, would be to filter by size. This filter is called variant length, and you have a few different size bin options. For this exercise, I used the traditional size definition for a CNV of 1 KB or greater and selected all those filters, reducing the results of my original query to 41. Another filter you might be interested in is the variant gene relationship filter. This is to help you narrow your results based on whether or not you're interested in variants limited to a single gene or that involve multiple genes. And there are currently 4 filtering options: single gene, which limits to variants contained obviously within a single gene, in overlapping genes, which limits to variants that fall within the region of overlap between genes that are indeed known to overlap, such as MYH7 and MHRT, spans multiple genes. That one limits to variants that involve more than one gene, and multiple genes, which is the combination of in overlapping genes and spans multiple genes. So using single genes might help you hone in on intergenic CNVs. So of course, you might want to use some additional filters, such as size or variation type if you want to remove the sequence variants from that. But you could also use spans multiple genes if you are indeed looking for larger CNVs. Another useful filter is variation type. This filter is also located on that left-hand menu we looked at earlier and includes a number of commonly used variation types, including those listed here. However, if you access this category via the advanced search, you'll find a few more options, including copy number loss and copy number gain. When using this filter, it's important to keep in mind where this piece of information is coming from. So variation type is a particular piece of information that's chosen by the submitter. It's not assigned by ClinVar. When submitting variants detected by chromosomal microarray with fuzzy endpoints, ClinVar recommends the use of the term copy number gain and copy number loss. However, you could definitely see how some submitters may inadvertently still choose the terms duplication or deletion to describe the same types of variants. So, of course, deletion and duplication can also apply to sequence level variation. The bottom line here is that when you use this filter, just keep in mind that selecting deletion or duplication from the commonly used filters on the left may result in some sequence variants remaining in your query. If you truly want to limit your search to variants identified on CMA with fuzzy endpoints, you might consider using copy number loss or gain from the advanced field, or simply adding in other filters such as size. Just to very quickly walk you through an example use case, say you wanted to know whether ClinVar had other deletion CNVs overlapping the same gene as one of your cases. For the sake of this demonstration, we can just use the gene SCN1A. First, start with a broad search of just the gene name. When we do that, you can see we initially get over 1,700 results. Since our case is a deletion, we can limit our search to other deletions using the variation type filter on the left. And you see this reduces our results to 228. At this point, we know we likely have some smaller sequence variants in these results, but it's really up to you whether or not you'd like to filter them out. You could consider limiting your search by size to just focus on those most likely to be CNVs, or you could limit by variant gene relationship depending if you are more interested in introgenic CNVs or multi-gene deletions. There are also several other filters you could use that we are not going to be discussing today, such as clinical significance, review status, etc. And finally, even though you now know how to search for CNVs within ClinVar using the typical web interface, it's often preferable to view CNVs in the genomic context. And while we probably don't have time today to go into this in extreme detail, I'll just mention that both UCSC and NCBI's Variation Viewer, those genome browsers host tracks displaying the structural variation within ClinVar. So in UCSC, you can find this using the ClinVar variance track, which I believe is under phenotype. And if you click on the to the page where you can set the parameters for that track, you can specify if you want to see only the short variants, only the long variants, both, and you can change the density of each, whatever you like. In Variation Viewer, these cases are contained in a track that's called DVAR Clinical Structural Variants in the study NSTD 102. And with that, I would like to acknowledge everyone who contributes to these efforts. Our group is always going, and I will apologize in advance if I left anyone off. And we have time for questions.
Thank you so much, Erin. Does anyone have questions? You can ask them now or type them in the chat box.
And of course, you can always feel free to email me later. It looks like, Jenny, there might be some coming up in the chat box if you want to read them to me, if you don't mind. Can you see them?
Here we go. Yeah. Okay. Yes. For the first one, it seems like there's confusion among some people misinterpreting haploinsufficiency dosage sensitivity reported in ClinVar for tumor suppressor genes as loss of one copy by itself is oncogenic. Which is not the case for most tumor suppressor genes. Does dosage sensitivity working group have any plans to try to educate people to decrease such misinterpretations?
Do we have anyone on the line from the hereditary cancer dosage group?
Yeah, this is Deb. I'm on.
Hi, Deb.
Yeah. So, I mean, do we have plans to educate? Yes, we would, in terms of ensuring that those are not those single somatic deletions, essentially, or CNVs that would be in ClinVar. But I really think this is a ClinVar question. So it's how are they planning to flag those so that it's more apparent that they come from a somatic CNV and not from an inherited one. So, yeah, I think it's.
Yeah, and I know, yeah, with the old display, they did kind of differentiate. They have kind of like a line essentially on the page showing the germline versus somatic. And I think that that's not as apparent in the newer display. And that's definitely some feedback that we have brought back to them. One other point, just to make sure everyone's clear, the dosage evaluations are available through ClinVar, but they're kind of like a side piece of information because, of course, ClinVar is observed variants and our dosage evaluations are just theoretical evaluations at the level of the gene. It's not really an observed variant. So they're just kind of pieces of FYI information on the side at the level of the gene, if that makes sense.
And I can't see who asked the question, so I don't, for some reason, I'm not seeing the chat up on my WebEx, but if that person wants to email to the I can send them the information to email to the ClinVar list, that it could maybe become a discussion, or at least get into their, ClinVar community call maybe at some point to discuss that.
Yep, and if you would like to do email, you can just email our generic ClinGen at clinicalgenome.org address. I'll get that, and I'll make sure that the ClinVar team sees that, and I connect you with Deb if you would like to connect with her as well.
Great, thanks. Erin, it looks like there was a question from Zoe Lewis that she sent to your chat privately, which I can't see.
I can see if I can move. There you go. Oh, is that you, Zoe? You want to just tell me?
Yeah. So I've noticed that some of the filters in ClinVar on the left-hand side are inaccurate, at least for our lab. And I don't know if there's a plan to improve those so that they more accurately reflect the variants in the database. Do you know?
Oh, goodness. Well, like, can you give me an example?
Yeah, Zoe, sorry, this is Deb. This is going to be a topic on the ClinVar call this Friday. So we have had the same issues. So I know, I'm sorry, Erin, this is not related to, the metric and the CNV, but it's a problem. It's a problem because we're trying to find this information in ClinVar, and using those filters, there is something going on there. And either they've changed, kind of like with how you told us about the kind of non-intuitive input to pull up a variant by a coordinate in the first place. It's either something like that. Maybe there's something we don't know in terms of the filtering. But Zoe, I totally confirm, and hopefully it will be something that is talked about on the ClinVar call. And I'm sending some search examples to their help email as well.
So is this going to be on for tomorrow, Deb?
I think so. I've needed to follow up with Danielle on it, and I have those searches, but I haven't. It's like on my to-do list today to send them to the ClinVar help.
Okay. Zoe, do you normally attend the ClinVar community call?
No, but I can.
You don't? Okay. Well, just either follow up. I think you know my direct email address. Either follow up with me or do that ClinGen at clinicalgenome.org, and we'll get you on the list for those calls if it's not tomorrow, whenever it is in the future, so you can be part of that conversation.
Okay. Thank you.
And Erin, there's a request to repeat how to look for CNVs in ClinVar.
Yeah, of course.
Thank you.
Let me go back to that. So yes, as Deb mentioned, it is not intuitive. It's not the way you normally do it in UCSC or other places. Let me go back. Okay, here's the cheat sheet.
Okay. Yeah, just while you're finding that, just to say, I will send around the link for the recording to the call as well, so that folks can listen again for any parts that you want to hear again.
Yep. So this is the syntax you got to do. Like, say your chromosome was like 2 or so. Do 2. Tell ClinVar that, hi, this 2 is a chromosome. And I would also like to look between these 2 numbers. So give it a number, a colon, another number, and tell it, hello, ClinVar, these are genomic coordinates, so please look across them and not just look for the literal number that you typed in. And so just to show you what that would look like in real life, it would look like something like this. Otherwise, if you don't do that, it just thinks you want to look for, these as written, and it doesn't understand what they are.
Thanks. Any questions about that? Or any other questions for Erin?
I don't have a question, but I do have a comment. So just this morning, I received an email from Genox and their interpretation tool called Franklin, that they have incorporated the ACMG ClinGen CNV guidelines to their interpretation. So that's really neat. I haven't used it yet, and I'm not sure if others have, but just wanted to bring that up.
Okay. And certainly if people use it and they like it, or, you know, is something we want to learn more. I mean, we could talk about, do we want them to show us this on a future Biocurator call? I don't know. But definitely if people use it and have thoughts, you know, let's talk about it.
Yeah, that's great, Erin. So any tools like that, if people have interest, we can certainly talk about those on this call, or, you know, have someone from that resource come and present to talk about all the features of the tool. That's helpful for folks.
Erin, this was a great talk. This is Marina. I just wanted to point out to everyone, this was brought to our attention recently, but OMIM actually links to dosage curation for ClinGen, both gene and dosage on the website.
They do. Let's see.
Yeah, to make you pull it up in real time, it's under the clinical resources tab on the right.
Yeah.
External links.
Pull up my favorite gene, which is ZEB2. And yes, if you come under clinical resources, you can also access our dosage and our gene disease validity. We'll just take you out to our dosage site. And that goes back to the ClinGen page.
Fantastic. That looks great. Any other questions for Erin? As I said, I can send a link for the recording around after the call.
Yep, and then again, that email address is clingen@clinicalgenome.org. If anyone has, wants to get on the ClinVar community call mailing list, or has any other specific questions, that comes to me. So that's easier to remember than my name address.
Great. Well, thanks so much, Erin. This is really, really informative, and just a lot of fantastic work in there. So thanks so much. And just a quick announcement before the call ends, just to let you know there's no call on February 13th, and that's in recognition of ClinGen's meeting-free week. So we won't have a call on February 13th, but we will resume on February 27th, and I'll be sending them details about that call in the near future. All right. So there's no other questions. We can say bye, and thanks again, Erin.
All right, thank you.
Thanks, everybody.
Bye-bye.
Bye. Have a good day.
Thanks. Bye.